तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So let us go back and look at a few of the problem sheets given earlier. We start with set 3, which was on the harmonic oscillator. I hope some of you have got copies, and after writing down the Schrodinger equation plus the solution and so on, there is a set of problems that is given. So let us go through these systematically. The first one refers to a particle in a box, the orthonormality condition, the completeness relation, etc. You are supposed to verify these, so they are just straight verifications. And then I have also asked for the momentum space wave function. So the problem was the particle in a box 0 to L, the energy levels were n squared pi squared h cross squared over 2m L squared, and the wave functions, the normalized wave functions, L, and n is 1, 2, etc. And you are asked to find the momentum space wave function corresponding to this, and that has also been written out here. Phi n tilde of p is equal to integral minus infinity to infinity the wave function is 0 outside the box. That is crucial to put in. Phi n tilde of p was equal to dx p x phi n of x, and this quantity here, the normalized value px, is 1 over square root 2 pi h cross e to the power, the convention we have is e to the I px over h cross, and the idea is to compute this quantity here. As you can see, if this thing had been just e to the I px or something like that, or a sine or a cosine or something like that from minus infinity to infinity, then this would be just a superposition of a discrete number of momentum states. But because the wave function gets cut off outside the box, it is localized to within this box. So on this x axis the particle does not ever go outside the box. So this means the uncertainty in the position can at no stage be bigger than L itself. Definitely it is inside the box, which means the uncertainty in the momentum cannot be smaller than h cross over L, of the order of h cross over L. So that immediately says that the momentum space wave function is actually spread out, unlike the position space wave function, and you can compute what this is once you put this in, and then take mod squared of this to find the momentum space, momentum density. Okay. In the case of the ground state, if you plot phi tilde of p mod squared, you would get something like this. There is a peak here and another peak here at these values, which are sin pi x over L. So the values p versus this quantity, and these would be h cross pi h cross over L. N corresponds to 1, so phi 1. Okay. I leave this to you to actually work it out. So it is an extended wave function in any case. The kind of general statement, if you have a function which is compact, which has compact support, then the Fourier transform has support from -infinity to infinity. The more you try to localize in position, the more it gets spread out in the momentum. Okay. So it is not a momentum eigenstate, that is for sure. Okay. In fact, there is a result given for this, it is cos squared PL over 2h cross, and then there is a rational function 1 over p squared minus something or the other squared, etc. It is easy to calculate the position and momentum uncertainties. You have to simply calculate some integrals here and then show that delta x delta p for any eigenstate n is certainly much bigger than h cross over 2, okay, including the ground state. Okay. The next problem was a particle moving freely in one dimension, but it was given on the position basis by a Gaussian wave packet. So the idea is to try to localize the particle near some point x0, and then the question is what happens to this as a function of time, and compute the momentum space eigenfunction, etc. So you are supposed to calculate delta x delta p, find the wave function at any instant of time greater than 0, find what the corresponding momentum space wave function is, the uncertainties, etc. Okay. In particular, for this wave packet, which is an interesting wave packet, psi of x0 equal to 1 over pi sigma squared to the power 1/4, these are normalization factors, e to the power minus some constant x, e to the minus x minus x0 whole squared over 2 sigma squared. So mod psi of x comma 0 squared is a Gaussian peaked about the point x0, something of this kind about the point x0. Okay. And for this Gaussian wave packet, you are supposed to compute the uncertainty in position, momentum, etc., and then show that at any instant of time x average is equal to x0 plus pt over m. So again, for this Gaussian wave packet, the center of the wave packet, the mean value of x, moves like a classical particle. It is a free particle. So classically the momentum is constant and x would be x0 plus pt over m, but now Ehrenfest theorem kicks in and you have expectation values moving according to this rule. Okay. You can do this by using directly by integrating or by writing down the Hamiltonian, which is just p squared over 2m, and using Heisenberg's equation of motion. Okay. You are also asked to find the spread of the wave packet as a function of time. This wave packet will spread, and the physical reason it spreads is because different components, different wavelengths do not travel at the same velocity. The wave velocity and the group velocity are not the same in this case, because the energy is dependent quadratically on the wave number. It is a free particle, so E is p squared over 2m and p is h cross k. So since and E is h cross omega, so omega is proportional to k squared, which means d omega by dk is not omega over k. That immediately leads to dispersion. Okay. The rest were some identities. In the harmonic oscillator, for the linear harmonic oscillator, what is the expectation value in any of the energy eigenstates? What is the expectation value of the kinetic energy and that of the potential energy? They happen to be equal. In the case of the harmonic oscillator, these two are equal, because that problem is extremely symmetric under the interchange of x and p in some sense. It is quadratic in x and quadratic in p. The Hamiltonian is very symmetrical. Okay. And then there were some Baker-Campbell Hausdorff type of identities. The only significant thing you must note here in this problem set is this thing here, is our definition of a coherent state. So an oscillator coherent state was defined in this following way, where alpha is any complex number, summation n is 0 to infinity, alpha to the power n over root n factorial n, where these were the oscillator eigenstates. Okay. And we know that A on alpha is alpha on alpha, alpha equal to any complex number. But you can also rewrite this in another form. You can also write this as e to the power minus a half mod alpha squared. We know that n itself can be found by taking a dagger and acting on the ground state, and therefore this becomes summation n equal to 0 to infinity alpha a dagger to the power n over n factorial acting on the ground state, because a dagger to the n on 0 divided by square root of n factorial is in fact the excited state n. So this is equal to e to the minus half mod alpha squared e to the power alpha a dagger acting on the ground state. Now we know the commutation relation between a and a dagger, so we know the one between e to the alpha a dagger and e to the alpha star a as well. And if you use that commutation relation or any of these relations which have been given to you earlier, this can also be written as e to the alpha a dagger minus alpha star a acting on 0. So there is a certain operator called the displacement operator. Really it should be E d of alpha comma alpha star, because these are linearly independent of each other, but just for convenience of notation I will call it d of alpha. This operator, which is the exponential of this combination here, acting on the ground state gives you the oscillator, gives you the coherent state. Now the reason this is called a displacement operator is the following. First of all, this operator is a unitary operator. That is easy to see, that d dagger equal to d dagger d equal to the identity operator. So its unitary transformation on the ground state gives you the coherent state. And physically what it corresponds to is the following. The wave function in the position basis corresponding to this alpha would be found in the usual way, which is x on alpha, and that would be x on n. And what is x on n? This is just the, by definition it is phi n of x, it is the normalized eigenfunction in the position basis by definition. And what is this equal to for the harmonic oscillator? Yeah, there is a Gaussian, so this is equal to e to the minus x squared over 2 in suitable units, in units of h cross over m omega or whatever. So really you should have m omega over 2 h cross and so on sitting here, okay, multiplied by the Hermite polynomials hn of x again in those units, and then there is some normalization constant an. 1 over 2 to the n factorial square root and so on. So to find this you have to put it in here and compute it, which does not look like a very trivial exercise, because you have to find ultimately, remember that if I put this in, you have to find alpha to the n and then hn, but now you use the expression for the generating function of the Hermite polynomials, and then this sum collapses and you can compute this sum, and the answer is again a Gaussian, but centered not at the origin like this one is, but centered at the real part of alpha. So it is again a Gaussian wave packet, but centered at the real part of alpha. What about the imaginary part of alpha? What would that correspond to? What would that correspond to? Would that play a role? Because I am claiming this is a Gaussian of the form e to the minus x minus alpha 1 whole squared over 2 and then other factors, but alpha, and there are phase factors and so on, but alpha 1 is a real part of alpha. What do you think is the role played by the imaginary part of alpha? It would be the center of the Gaussian wave packet in the momentum space wave function, because you know that the momentum space wave function is a Fourier transform of the position space wave function. The Fourier transform of a Gaussian is a Gaussian once again. So alpha 2 would appear, if you did p with alpha, you would get p minus alpha 2 and so on, etc. What does that imply physically? Finally, what does it imply? Says a Gaussian wave packet has been essentially shifted in the sense that classically the harmonic oscillator, classically not quantum mechanically but classically, would correspond to an elliptic orbit of this kind in x and p. This is an oscillator oscillating about the point 0 0 in x and p. The equilibrium point is at 0 0. Once you apply this displacement operator e to the alpha a dagger minus alpha star a, you get a new state which is also again an oscillator but would correspond to something like this. It is simply shifted from this point, it is displaced from this origin to a new equilibrium point. This is alpha 1, that is alpha 2. That is why this D, I have used the symbol D, and that is why it is called the displacement operator. It displaces this oscillator. What is the uncertainty product delta x delta p for the ground state of the harmonic oscillator? It is exactly h cross over 2, it is a Gaussian wave packet, so it is the minimum uncertainty state, but so is every coherent state. For arbitrary alpha it is again Gaussians, so once again the uncertainty product is a minimum value. In fact, if you plot delta x versus delta p, this quantity in units of square root of m omega over h cross, this quantity in units of 1 over square root of units of square root of m omega h cross, then both these are dimensionless quantities, and delta p delta x must be greater than or equal to half. Equal to half is this hyperbola. And symmetrically at this point 1 over square root of 2 for each coordinate, each of the two, this is where the ground state of the harmonic oscillator is, and this is where all coherent states are. For all of them you have this minimum uncertainty with this symmetry between x and p. The excited states would be in the harmonic oscillator delta x n delta p n equal to n plus half h cross. So the ground state n equal to 0 is half h cross, and the excited states, I have set units such that h cross disappears on both sides, those guys would correspond to the states here, here, etc. Okay. Square root of 3 over 2, square root of 5 over 2 and so on. Okay. You could ask what happens if I took this, what happens if I took this e to the alpha a dagger minus alpha star a, I apply it on 0 and I get equal to alpha, coherent state alpha. What happens if I applied this not on 0 but on an excited state itself, some r? Ask what happens then. The same operator acting on an excited state of the oscillator. This is called a generalized coherent state. It has very, very interesting properties. They are not minimum uncertainty states, even the ground state is not, and these guys are denoted in this thing, and it is called a generalized coherent state. They again have a lot of applications in quantum optics, which we will not get into here. What is interesting to note is that these operators, d of alpha, d of some other alpha, alpha prime, they have an interesting multiplication property among themselves, and that has been given here as an exercise, I think, to verify. Yes, I have given d of alpha, d of beta is equal to d of alpha plus beta, d to the I imaginary part of alpha star beta. So this is alpha beta star. It is fairly straightforward to verify this relation here. This is again another way of writing the Weil commutation relation between x and p, the Weil form of the commutation relation. Recall that earlier when we said x commutator p is IH cross unit operator, what is e to the I AX, e to the I BP, where a and b are numbers, ordinary numbers, and that again had a form similar to this. A and A dagger, if you like, are linear combinations of x and p, non-Hermitian of course. So this is essentially the same Heisenberg algebra being rewritten in different ways. Okay. The important point about the coherent states is that they are not orthogonal to each other, and this is crucial, because alpha beta mod squared, and there is an expression, a simple expression for this. This is mod squared of this is e to the minus mod alpha minus beta squared. So certainly it is normalized. If alpha is equal to beta, you get 1, that is for sure, but otherwise it is not 0. These are not orthogonal states. They are an over complete set. It is not a complete set, they are an over complete set, and they are not orthogonal to each other. Okay. The last problem, the next problem in problem set 3 was on finding the time dependent propagator for the simple harmonic oscillator. So here I said let us go back to the actual time dependent Schrodinger equation and try to solve this equation completely by using a Green function for it, and that is what I call the propagator. So let us write it down. And this was, you were just asked to verify this because it requires a little bit of mathematics to work it out. So the equation was delta psi delta t x comma t equal to minus h cross squared over 2m d2 psi over dx2 plus 1/2 m omega squared x squared psi. And now the point is, if you specify adequate boundary conditions, and in this case we want the wave function to be normalized, so that means psi of x comma t must go to 0 as x goes to plus minus infinity, together with an initial condition, then it is possible to write the solution at any time as integral over this dx prime, and then a kernel which is a function of x, x prime and t, psi of x prime and 0. This quantity is called the propagator because it helps you go from the wave function at time 0 to the wave function at any later instant of time, okay. And it is called the Feynman propagator. And I have given an expression for the propagator here, a fairly complicated expression, and the idea is to find out, is to verify that this is true or not. By the way, what is the propagator for the free particle? Suppose you had no oscillator at all, what does the propagator look like? What is the propagator for the free particle moving on a line? I mean, no, what is it, what is the propagator? Yes, but what is that equal to? What is that explicitly equal to? So we do not have this, there is a free particle propagator, no potential. Certainly you can still write the wave function at time t in this form. What is this propagator equal to? How would you do it? A good way to solve this problem, it is an initial value problem, right. You are interested in psi of x comma t for all t greater than or equal to 0. You are given psi of x at t equal to 0 and you are trying to find what it is at later instance of time. So you are interested in only the half line in t, namely t greater than 0. It is a first order differential equation in t. So what is the automatic thing to do? What Laplace transforms, you would use Laplace transforms. And what would you do for the x variable? That is defined minus infinity to infinity. Yeah, Fourier transform. So you do a Fourier transform in x, a Laplace transform in t, and the job is done. You compute what the solution is. What do you think is going to happen? That is the free particle propagator. We could do this very painfully, but you can see very easily that if you took a Laplace transform in t, this is going to have, if the s is the conjugate variable to it, this is going to be s times the transform minus the initial value, okay. And if you do a Fourier transform in x and k is the conjugate variable, differentiation with respect to x corresponds to multiplication by k. So it is clear that the transform is going to have a k squared multiplying it and it is going to have an s multiplying this, and there is an inhomogeneous term, okay, right. So eventually this transform is going to be 1 over some s plus k squared or s minus k squared, whatever, acting on the initial value, okay. And the inverse transform of that is an exponential. So it will have an e to the minus k squared, which is a Gaussian in k, and if you take the inverse transform of a Gaussian, you would get an e to the minus x squared. So I expect in this problem that I am going to get something like e to the minus x squared over t acting on the initial state. That would be my transform. Are you familiar with the diffusion equation? Yes? You studied the diffusion equation? Well, we know the solution to that. Let us write that down, and then I will write this down by inspection, because remember the diffusion equation says delta rho over delta t for any concentration rho is d times d2 rho over dx2. That is the diffusion equation. And what is the solution to this diffusion equation? If you start with a source at some point x prime, so if you say rho of x comma 0 equal to some delta of x minus x prime, some special point x prime, you have the entire molecular species is concentrated at some point x prime, and then you let it diffuse as a function of time. The answer is some kind of Gaussian. Then rho of x comma t is 1 over square root of 4 pi dt e to the minus x prime squared over 4 dt. That is the standard solution to the diffusion equation. So it says if on the x axis you start with an initial concentration at the point x prime, as a function of t, after some time you are going to get this, and then it is going to get widened out and so on. So it is a Gaussian concentrated about that point there. Well, this equation looks pretty much like that, because this minus h cross squared could be written as IH cross squared, right. So it is essentially the same equation on both sides. So let us write this as minus h cross squared and bring the I h cross here, so this goes away and there is a 1 over I here which gives you h cross. It is the same solution if you like. So this means that if the initial particle was concentrated at the point x prime, that Gaussian is the solution, but if it is concentrated, it is given by a distribution by itself psi of x prime 0, all you have to do is to put this corresponding solution in here. So let us put that in, e to the minus x prime whole squared over 4 times d. Now what is d? D in our problem is I h cross over 2m. It is imaginary, it is not real diffusion, of course, it is just the Schrodinger equation. So let us put that in, over 2, that makes it 2 t and then m. Had this been some initial point t naught, then this would be just t minus t naught for all t greater than t naught. And then the normalization, so let us put that in, square root of 4 pi d is I h cross over 2m root m by 2 pi I h cross. That is the exact solution to the time dependent Schrodinger equation for an arbitrary initial distribution. You specify any psi of x prime 0 and that is the solution at time, any time t greater. This quantity, this thing here together with this factor, this is called the propagator. In this case the free particle propagator. So notice actually what I have done. What I have done in writing this solution out here is exponentiating the second derivative operator. This is really what I have done, because it says pretend that the right hand side is just some number, then it says delta rho over delta t equal to some lambda times rho. Lambda is an operator which acts on the x variable, etc., but the solution here is rho at time t equal to e to the lambda t rho at time 0. So going back to the original x variable, it says rho at x comma t equal to e to the power d d2 over dx2 rho x comma 0. So the question is, what is this equal to? If this were d over dx, what would this be? If this were a first derivative, then you can use Taylor's theorem and this would be just rho of x displaced by d or something like that. There is a t, sorry, dt. dt has dimensions of length squared, so this is dimensionless. So this fellow would just be, if this were root dt d over dx, this would be just x plus square root of dt. But when you have a second derivative, then the answer is it is some integral operator, because it must depend on all x, because all derivatives are acting on it, arbitrarily high orders. Therefore it must depend on rho, not just at one x but at all sorts of places, and it becomes an integral operator whose kernel is given by this, precisely by this. So that is the reason why you get this Gaussian multiplying this psi and then an integration over x prime, because you are really exponentiating the second derivative operator, and the answer is that it is an integral operator and the kernel is a Gaussian. Now for the harmonic oscillator you are exponentiating not just d2 over dx2, but you are exponentiating the operator d2 over dx2 plus x squared, and those two parts do not commute with each other. So this Green function we wrote down, this propagator, is a very non-trivial object and it is not always possible to write it down for all problems. The path integral way of doing quantum mechanics starts at this point. It really tells you how to find these propagators by what is called time slicing, but we are not going to do that in this course. However, this expression for the harmonic oscillator's Green function is sufficiently important that you need to know how to, at least to verify that this expression is valid here. So that was the reason for giving it. Okay. Then so is this idea clear about the propagator, what I meant by the propagator? The idea is that you give me the Schrodinger equation and you specify the initial wave function, then the future wave function is obtained by some propagator acting on the initial wave function, okay, which takes you from the point x prime, any point x prime, to any other point x. Okay. Okay. Then the next question once again had this Hamiltonian, harmonic oscillator Hamiltonian in suitable units plus lambda a plus a dagger in suitable units. What does this Hamiltonian correspond to? What does it actually correspond to physically? Lambda is a real constant. What would it correspond to? And then you are asked to find the eigenvalues of this Hamiltonian. What would you do? Remember, so what does this correspond to? Well, one way to do it is to, we are asking what does it correspond to physically, so we should go back to the physical variables x and p. If you go back to the original variables, this was equal to half p squared plus half x squared. We have set h cross as 1 and omega is 1 and m is 1 and so on, plus some constant lambda a plus a dagger. But what is a plus a dagger? Yeah. A plus a dagger is root 2 x, so this is equal to, what does that correspond to? Pardon me? Yeah, but physically what has been done to the oscillator? You put a constant electric field, right? Or if it is a spring in which things goes up and down, you have added gravity to it. So what has it done to the center of oscillation? It just shifted it. So all that has been done is to shift the center of oscillation. The potential is no longer like this, but this potential has gone over to something like this. All that has happened is you have shifted the oscillator. So would you expect the energy levels to be changed? You would not expect the spacing to be changed, but certainly there is an added constant. So what should you do? You should complete squares in this case. So you complete squares and then you end up with some x prime equal to, so this is equal to minus some constant. So all you have done is to shift this some other position and you got a potential like this. So this constant is minus a constant, this is the constant, you change the energy levels by adding an overall constant, and once again it is just half h cross omega, it is just h cross omega, equal spacing completely. So this problem is trivially solvable, trivially. It is just a linear perturbation on a quadratic Hamiltonian and it is trivially solvable in this case. Okay. So that is why I said this is a trivial problem. What value should lambda take in order that the ground state energy be exactly 0? Well, you can fix this, right? You know what this quantity is, you know how much you are going to add, that depends on lambda, and that must be exactly equal to half h cross omega, in this problem half. So once you fix that, then the ground state energy is exactly at 0. So that is a trivial problem. The next one was the problem of particle in a constant, free particle in a constant field of force. So the potential was minus Fx, and I worked this problem out explicitly in class. So this corresponds, you can't quantize, you can't the solutions in the position basis are airy functions, but the solutions can be written down in terms of the momentum basis. The equation is easy to solve because the Fourier transform has things like e to the power, the p cube term and a p term, that is trivial to solve, and the normalization is an energy normalization. So that was for problem set 3, and then in set 4 we went ahead with it. Now there were problems on the harmonic oscillator eigenfunctions themselves. One of the points I wanted to point out was the following: the differential equation satisfied by the position space wave functions in the harmonic oscillator and that satisfied by the momentum space wave functions are exactly the same in suitable units, they are exactly the same. Therefore the solutions are exactly the same in functional form. The solutions in x, if you put in the appropriate constants and so on, then the solutions in x are of the form phi n of x. These go like some normalization constant e to the minus x squared over 2 and then hn of x. In the momentum basis, phi n of p tilde for the same state, the same eigenstate, these fellows would go like some an e to the minus p squared over 2 hn of p. Okay. So the functional forms are exactly the same. On the other hand, I know that the momentum space wave function is the Fourier transform of the position space wave function. So I know also that phi n tilde of p equal to the Fourier transform of phi n of x. Phi n tilde is a Fourier transform of this guy, and this is equal to integral dx e to the I px over root 2 pi setting h cross equal to 1 times phi n of x. So I could regard this as an integral operator with kernel e to the I px acting on a function in L2 to produce another function in L2, because this 2 is square integrable. This is normalized to 1, mod phi n of p whole square dp is 1, and so is mod phi n of x, and we know that the Fourier transform of an L2 function is also L2. In this case we got something better. It says phi n of p has the same functional form as phi n of x, exactly the same functional form. So this is like an eigenvalue equation, and apart from an overall multiplicative constant whose modulus is 1, this and that are exactly the same. This is some other function, modulus of an is modulus of an prime. So apart from that, these two are exactly the same function. So it says that these functions are something special. They could also be regarded as eigenfunctions of the Fourier transform operator. because you act on you take the function and you do a Fourier transform on it, you get another function in the same space, it is again in L2, but that function has the same form as the original function, therefore this is an eigenfunction of the Fourier transform operator, and the eigenvalue must have unit modulus. So in general the eigenvalues with some complex number of unit modulus. Yeah. Okay. Now what about the Fourier transform of Gaussian? It gives you exactly the Gaussian, and in fact if you work with the ground state H0 is 1, you discover that it is equal to itself in functional form. So the eigenvalue is 1 in this case. So the ground state in fact has eigenvalue plus 1. So the ground state wave function of a harmonic oscillator is also an eigenfunction of the Fourier transform operator and has eigenvalue plus 1. What about the excited states? Well, the first excited state you will discover phi n tilde of p in functional form is I times phi n, phi 1 tilde of p is I times phi 1 of x, which implies that it is an eigenfunction of the Fourier transform operator with eigenvalue plus I. The next excited state would have minus 1 as the eigenvalue, the third excited state has eigenvalue minus I, and the fourth one comes back to plus 1. And this is because the fourth power of the Fourier transform operator acting on functions in L2 is the identity operator. So f to the power 4 f equal to f itself. You can verify this. In fact you can verify that f squared acting on f of f squared f of x equal to f of minus x. In other words, the square of the Fourier transform operator is a parity operator. So you take a function of x, you do the Fourier transform of the Fourier transform, not the inverse, once again Fourier transform of the Fourier transform, and you get f of minus x. That is easy to verify. Therefore you do it 4 times, you get back the original function. This immediately suggests that the Fourier transform operator itself has eigenvalues equal to the 4th roots of unity, 1 I, minus 1 and minus I, and the harmonic oscillator eigenfunctions, the energy eigenfunctions, are also Fourier transform operator eigenfunctions, such that the ground state has eigenvalue plus 1, first excited state I, second excited state minus I, third excited minus 1, third excited state minus I, fourth one back to I 1, and it keeps going. So this is an extremely interesting property of these functions. There is not arbitrary functions, as you can see. This symmetry between x and p gives you some profound insight into what is happening with regard to the Fourier transform operator itself. Well, the obvious question to ask is, if these functions are the eigenfunctions of the Fourier transform operator, then the Fourier transform operator is like the square root of the parity operator, and the parity operator is like the square root of the unit operator, then what about the square root of the Fourier transform operator? Would the harmonic oscillator eigenfunctions also be eigenfunctions of this operator with eigenvalues at the 8th roots of unity on the unit circle, and so on? Then you can ask for the square root of that operator, the 16th roots of unity, and so on. I leave you to verify whether this is true or not. It is an interesting exercise in mathematical physics to verify if this is true or not, and it has implications in other areas of mathematics, but we will not go into that. But up to the level of the Fourier transform operator, I have given here what the expected answers are, so please check that out. Okay, I should stop here. The last 2 questions had to do with the reflection and transmission. These are things I have already done in class. I have just written them down systematically here so that you have the exact formulas with the correct notation and so on. And finally the last question is an extension of the uncertainty principle. I already mentioned that delta A delta B, if you had two arbitrary operators, then delta A squared delta B whole squared is greater than equal to 1/4 the expectation value of the commutator of A with B squared. This was the generalized uncertainty principle I mentioned, but you can actually, where A commutator B is some minus IC or whatever it is, where C is a Hermitian operator, but you can also ask what is the exact relation, and it turns out that it should be greater than equal to this commutator squared plus a similar expectation value squared of the anti-commutator, and since that is again a non-negative quantity, you play it safe by saying it is certainly bigger than this. So there is an extra term in here, it is actually bigger than this plus another term here which could be 0 under certain circumstances, and that is the actual best result that you can get. That is the generalization of the uncertainty principle, it is an extension of the uncertainty principle. I believe it is called the Schrodinger-Robertson uncertainty principle. I can't swear to that right now because I do not remember for sure, but that extra term is sometimes used also and plays a role. Okay, so that should take care of these problem sets, and please go through these completely, make sure you solve all of them. If there is any problem, just let me know. Okay, so let me stop here.